Okay, so we want to introduce the concept of line integrals, and we're going to introduce it with the following problem. So let's say there's a wire um, that is on the ground. The on the ground part isn't so important, but it's lying on the x. It's lying in the x and y plane. Let me try that again. Okay, so this is the x-axis. This is the y-axis. It's lying in the x and y plane, and it kind of follows this curve. And the parameterization of this curve is r of t is equal to x of t, y of t. And this is a wire that has variable mass density. So in other words, we could say like maybe the diameter of the wire is changing as you go along this way or something like that. The mass density of the wire is given by the function f of x of t, y of t. And the units would be something like kilograms per meter. So the question that we want to ask is, what is the mass of the wire? Okay, now if the wire were constant, if the wire had constant density, in other words, if the f function here was always equal to say 17 or something like that, then the mass of the wire would just be 17 times the length of the wire. But we are in a more complicated situation here where the mass density changes as you move along the wire. Like I said, for example, it could be that the thickness of the wire is changing, so the mass density of the wire is changing, okay? Or it could be made from different materials. So it might be made with a heavier material here and a lighter material here, and it kind of is blended in between. Now, whether or not this is the most practical problem isn't really what I want to talk about now, but this is just the setup for the problem. This is what is going to motivate the concept of line integrals. So to do this, the first thing we're going to do is try to estimate with this sort of Riemann sum. Okay, so the idea then is along this curve, we're going to kind of break it up into a bunch of smaller subcurves like this. Okay, now if I say take this piece of the curve, I'm going to try to zoom in on it, just this part of the curve right here. I'm going to try to zoom in on it over here. I mean, not literally zoom in on it, but just sort of draw what this would look like over here. So it's going to look something like this. Okay, so this is one segment. This segment right here is just this part right here. Okay, and what we want to do then is call this distance here, we're going to call this delta x, and we're going to call this delta y. And so the idea is that if we divide this curve up into smaller and smaller pieces, this curve right here is going to look an awful lot like the hypotenuse of this right triangle. Okay, and so what I'm saying is that the length, that length of the curve is approximately equal to the square root of delta x squared plus delta y squared. That's just the Pythagorean theorem. And as we divide this curve into smaller and smaller in pieces, that approximation is going to get better and better and better. So let's say that this point right here, uh, is something like x1, y1. This point right here would be something like x2, y2, so on and so forth. Then the mass of the wire between the points x1, y1, and x2, y2 is approximately f of x1, y1. So we're treating f as being constant on this on this part of the wire from x1, y1 to x2, y2. We're treating f as being constant, and we're treating the length as basically being the length of this hypotenuse right here. So then the mass of that wire is just the constant mass density times the length of the wire. So what it means is that the mass of the wire going from x1, y1 to x2, y2 is approximately this number right here. Okay, and so now what we want to do is we just want to add all of those up for all of the intervals. So let's say it starts at x1, y1 and goes all the way up to, let's say this point right here is x n plus 1, y n plus 1. Then the mass of the wire, the mass of the wire is approximately the sum from I equals 1 to n times the square root of delta xi squared plus delta yi squared. Okay, that's just adding up the approximate mass of each one of these individual subcurves. Okay, now the idea then is that as n goes to infinity, this is going to converge to a certain integral. And the integral that it converges to is going to be the following integral. This converges to the integral from t equals a to t equals b of the function f of x of t, y of t times the square root of x prime of t squared plus y prime of t squared. Well, we know what all of this stuff is. F is just the function that we're given. X prime of t comes from the derivative of this. Y prime of t comes from the derivative of that. A and B, what we're saying is that this point right here is R of A, and this point right here is R of B. So in other words, R of A is equal to x1, y1, and R of B is equal to xn plus 1, yn plus 1. So in other words, what this tells us is that given this situation, the answer to this question, what is the mass of the wire, is just equal to this integral right there. Okay, and as the class goes on, we'll look at more examples of how to actually do these computations.